Context-free grammars and syntactic analysis. Sentences look like sequences of words, but their structure is much richer. Sentences involve words closely associating with each other to form phrases. Those phrases in turn associate with other phrases or words to form larger phrases, and we keep on going until we have the largest phrase of all, the sentence. In this section of the class, we're going to be using formal grammars to describe these phrasal arrangements, and we're going to get formal grammatical descriptions that will not only give us a more satisfactory account of the kinds of configurations of words that are possible in language, but also considerable inroads into other types of interfaces between the structure of sentences and other features of language and cognition, including meaning, prosody, and other areas. So let's start off with definitions. A context-free grammar consists of a tuple with the following components and characteristics. First, we have a finite set of non-terminal symbols, n. We have another finite set of symbols, which are terminal symbols. We'll call that v. There's a designated symbol in the set of non-terminal symbols, which is what we call the start symbol, which is going to be corresponding to the highest level of organization of whatever word sequence we're describing. And there is a finite set of rules. And each of those rules has the form of some individual element in the non-terminal symbol set rewriting to a sequence of symbols that may be terminals and or non-terminals. And so a rule is written of the form x goes to alpha, where once again x is an individual non-terminal symbol and alpha is a sequence, which is possibly empty and possibly non-empty, of symbols drawn from the non-terminals and terminals together. And we'll sometimes read this as x goes to alpha. And a context-free grammar derivation is the recursive expansion of non-terminal symbols in a string by rules in the rule set. And we start with the start symbol and recursively rewrite it until we have nothing else but terminal symbols left. And the derivation tree, T, which we're going to make a lot of use of here, is the history of the rule applications. So let's see how this looks. Let's take an example grammar, and what you'll find is that although I described all these components that we have, usually it's enough to just list a set of rules, and then the components, the breakdown, are going to be obvious from the rule set. So in this case, our grammar is this set of 10 rules, and I'm just going to read them off for familiarization. S goes to NP-VP, which I might gloss as an S is for sentence. So a sentence can consist of an NP, which will be a noun phrase, and a verb phrase, a VP. NP goes to determiner noun. An NP alternatively can go to NP-PP. A PP, prepositional phrase, can go to, that is, it consists of a preposition and a noun phrase. A verb phrase rewrites as V, verb. And then those are the rewrites of what we might call phrasal categories. And that's not a formal designation, but it is an informal distinction between categories that have words on the right-hand side in their rewrites and categories that don't. And you'll see this a lot. This is an instance of that. Then on the right-hand side of on the right-hand half of this screen, we see the rewrites that lead to terminal symbols. Determiner rewrites as the, noun can rewrite as dog, noun can also rewrite as cat, preposition can rewrite as near, and verb can rewrite as growled. So if I were going to go back in the definitions of the previous slide and ask what are the pieces of this grammar, I would say here the non-terminal set is the categories S, NP, VP, det, NP, and V. Those are all things that appear on the left-hand side of some rule. The terminal set is a set of categories that don't appear on the left-hand side of some rule. So that's the, dog, cat, near, and growled. And our start symbol, by convention, is often going to be the left-hand side symbol in the first rule that's listed in the grammar. That's just by convention. Okay, so now let's connect that to derivations and derivation trees. So we have, once again, at the top of this slide, the grammar that we defined, and here is a derivation, which is going to be, once again, a recursive sequence of rule applications starting with the start symbol, and I'm going to rewrite those. So the first thing that I have to do is, since I have the start symbol, I have to rewrite it using some rule that has that start symbol S on the left-hand side of the rule. Well, there's only one rule in this case, S, that has S on its, there's only one rule in this case that has S on its left-hand side, so I'm going to rewrite using that rule. And so I rewrite S as the sequence NPVP. And so now the tree that I'm showing, iteratively expanding, is just a history of the sequence of these rule applications, but the active parts of the tree that still need to have rewriting applied to them are the ones which are non-terminal categories and that are at the frontier of the tree. And that's NP followed by VP. So let's keep on going. I will choose, in this case, I could choose either of the two NP rewrite rules that we see up here, but I'm going to choose the first one, or I'm going to choose the NPPP rule here. So I'm going to rewrite NP as NPPP, and now I have note, a sequence of 3 non-terminal categories on the frontier of the tree, NP, PP, and VP. And so that's what I've got left to rewrite. I may choose then, for example, the other NP rewrite rule now for the first NP, and I might rewrite that as a determiner noun. Now I have a set of 4 non-terminal symbols to rewrite. Now let's look at the word. Let's look at the symbol determiner. So that only has one. Det has only one rewrite rule, so I have to rewrite it to the. N I could rewrite to dog or cat. Maybe I'll rewrite it to dog. PP I will rewrite it to PP, P and P because there's only one choice there. P has to rewrite to near in this grammar. NP, once again, I have some choices. Maybe I will choose the NP goes to determiner noun case here. Determiner goes to the, and maybe goes to cat in this case. And VP has to go to V, and V has to go to growled. And now I'm done. So I now have a sequence of terminals. The frontier of the tree is entirely terminal, so I know that I'm done. And the sentence that was generated was the dog near the cat growled, and the derivation tree is this structure here, which contains information about the structure of the sentence that we're going to get into later. So we can ask some questions about a context-free grammar, including, for example, how many strings does it produce? How many trees does it produce? And is it ambiguous? And in the general case, just as a side note, this last of the 3 in the general case is undecidable. So there's no guarantee that you can even determine, that you can even compute the answer to whether a context-free grammar is ambiguous. But with some context-free grammars you can. So I'd encourage you at this point to go back and look at the grammar that we just covered and ask, what is the answer for each of these 3 cases? How many strings can the grammar produce? How many trees can the grammar produce? Is the grammar ambiguous? So I encourage you to stop here at this point and take that as an exercise. But before I finish this segment, I want to just flag a high-level consequence of this formal means of generating strings. So I talked about the derivation tree as a history of the rule applications. There's a lot of power in that derivation tree in terms of developing a theory of linguistic structure at the level of how words combine with each other, that is, syntax. In particular, the nodes in the derivation tree offer what we call a structural description of the syntax of the generated tree, a generated string. And in generative grammar, which is the broadly understood is the enterprise of defining formal accounts of fragments of natural languages using grammatical mechanisms like what we're looking at, this structural description is the phrase structure of the string. And these structural descriptions will play a role in the theory of linguistic structure and meaning. So, for example, syntactic regularities, it turns out, are often theoretically stated in terms of these structural descriptions. By what I mean by syntactic regularity is another constraint or generalization about what structures are okay in the language, and as a result, what strings are in the language. Additionally, within the broader theory of syntactic structure, linguistic structure, phrase structure also interfaces with other levels of representation. So, for example, we'll see an interface with prosody, which is the intonational contour and durations and breaks that are natural to put in language and when you speak, and also meaning composition, how phrases mean what they mean. So we'll take a break now and come back and look at all of these things going forward.